Okay guys, so today we're going to be looking at a concept called concavity of a function. So we've already used the first derivative, and that first derivative has helped us to figure out where we have high points and low points on a graph or on an equation. Concavity means something completely different, and concavity is based off of the second derivative rather than the first derivative. Concavity means the curvature of the graph. So here's the first part of it. It says let f be a function whose second derivative exists on an open interval I. If that second derivative is greater than 0, meaning if the second derivative is positive for the x's in some interval, then the graph is going to be concave up. Here's the way a concave up graph would look. Just a simple parabola. That's always concave up. What could be the equation of a parabola? Y equals x squared, right? And if I take the first derivative, I would get 2x, and if I took the second derivative, I would get 2. Do you see how the second derivative would always be positive? So that's one way I would know that this parabola, this y equals x squared, is always going to be concave up. Let's take another function, one that's concave down. This function, what's it going to be? Y equals negative x squared. So the first derivative then is negative 2x, and the second derivative is negative 2. See how the second derivative is always negative? So that means that this function here that we started with is always going to be concave down. So not all functions, though, are always concave up or always concave down. Sometimes we have a combination. If we have a function that looks like this changes concavity. It's concave down, and then it switches to concave up. This point right here has a special name. That point is called the point of inflection. Inflection just means a change of the concavity. So the reason that's called a point of inflection is because we're going from being concave down, and then right at that point we switch to being concave up. So the other thing I would know is that the second derivative would be negative over this interval where we're concave down. And then it would be positive over this interval where we're concave up. So the first thing we're going to do is just look at an example, and we're going to state the intervals on which the graph is concave up or concave down. I can see that until I get to right about here, that function is concave up. So it is concave up from negative infinity. Remember, we're using x's when we talk about an interval. From negative infinity until we get to this x value. What's that x value right there? Negative 1. So it's concave up over that interval. Right here, this little section, that would be concave down right there. So the function is concave down over the interval from just negative 1 to 0. Right here in this little section, what do you think that concavity is? Concave up again, and that is from 0 to 1. And then here it switches again. So right in there, it's going to be concave down from 1 to infinity. So this point right here, that point right there, and that point right there are all points of inflection. If they're points of inflection, what do you think the second derivative would have to equal at a point of inflection? 0, right, Chad? That's because if it goes from being a positive on the second derivative to a negative on the second derivative at that point of inflection would have to be just 0. So here's the way we find points of inflection. First of all, we talk about possible points of inflection. These are the values of x which make the second derivative equal 0, or for which the second derivative does not exist. But if the second derivative does not exist, we have to check, was it really just a vertical asymptote, or is it truly a possible point of inflection? Remember, a vertical asymptote wins out over everything. If you've ever played euchre, it's like the trump card. You know, if you play trump, that beats everything else. All right? So that's the way a vertical asymptote works. A vertical asymptote is going to beat out a possible point of inflection, and it's going to beat out a critical number. Okay? All right, so let's look at example 1, and let's try to find the points of inflection, to find the concavity. So rather than using the product rule, I could just multiply this out and get x to the 4th minus 4x cubed. So I'm going to have to take the first derivative. Teresa, what's the derivative? And then right. Okay, and now we also have to take the second derivative. Brittany, what's the second derivative?
12x squared minus
24. So once we have our second derivative, we're going to set it equal to 0. Because when that concavity is 0, that's going to be a change in the curvature of the graph, or the concavity of the graph. So I'm going to do 12x squared minus 24x equals 0. I'm going to factor out a 12x, and I'm left with x minus 2. So what are my possible points of inflection? What makes this equal 0? 0 and 2. I'm calling these possible points of inflection. I don't know for sure if they are. It's just like when we did the first derivative test. The critical numbers were possible maxes or mins. We didn't know for sure if they were until we did the first derivative test. The test we're doing now is called the Concavity Test. We're testing to see if these possible points of inflection are indeed points of inflection. So I need to go from negative infinity to 0, 0 to 2, and 2 to infinity. I need a test value in each of these intervals. Give me a test value for this interval, -1. We're going to plug that not into the first derivative. We're trying to figure out the concavity. So we plug -1 into the second derivative. Plugging it in here, I get a negative times a negative, so this is going to be a positive. So it's concave up. In this test interval, I can use 1. Plugging 1 into my second derivative, a positive times a negative is going to give me a negative, so I'm going to be concave down. Right here, I'm going to get the number 3. So when I plug this into my second derivative, I have a positive times a positive. That's going to be a positive. So we're going to have concave up. So if our function goes concave up, concave down, concave up, are these possible points of inflection? Is that where the concavity is changing? Yeah. Here's what's happening. We're going concave up, concave down, concave up. So it's going to look something like that. Shouldn't a quartic function look like that? Have that end behavior in the same direction? So therefore, we have points of inflection, not possible points of inflection. We've proved that they are points of inflection at 0, comma. Where do I substitute in? The original. I'm trying to find a point. So back into the original is 0, 0. 2, back into the original, wherever you want, this version or this. That's 16 minus 32. That's going to be -16. And so those are the points of inflection. So I could then know that that point right there is 0, 0. And this point right here is 2, -16. Of course, this is not drawn to scale, but we have some general idea of the shape of the graph. All right, example 2. Given the information below, state the domain, the points of inflection, and the concavity. This was a pretty tough one to take a derivative of, and I'm not really testing you anymore to see if you can take derivatives all the time. So I just went ahead and got the derivative for you. Here's the first derivative, here's the second derivative. Now, first of all, though, we want to state the domain of the original function. We have a radical x in the denominator. Are we allowed to have 0 in the denominator? Are we allowed to have a negative under the radical? No. So therefore, the domain of this function is going to be from 0 to infinity. So when I do my test interval, I'm not going to start it at negative infinity. I'm going to start it at 0. I can't check negative numbers because they are not in my domain. So now I'm going to look at the second derivative. So we're trying to find our possible points of inflection. So we want to know what makes this equal 0 and what makes it undefined. So first of all, what would make this equal 0? 3 minus what is 0? 3. So our possible point of inflection is 3. But if I set the denominator equal to 0, I get 0. Is 0 also a possible point of inflection? No, because it's not in our domain. So it cannot be a possible point of inflection. A lot of times we think that that would be a vertical asymptote. And if it were just an x and not a radical x, it would have been a vertical asymptote. So our only possible point of inflection is 3. Those are going to be our intervals. I didn't give you a place to put the test value. If you want to just put it right here to the side, you can. Just showing you another way you can create the chart. I'm going to plug 1 into my second derivative. Square root of 1 is 1. 1 to the 5th is 1 times 4. That's going to be positive. 3 minus 1, that's positive. So therefore, we're concave up. 4, square root of 4 is 2 to the 5th is 32 times 4. That's going to be positive. 3 minus 4, though, is negative. So that's going to be concave down. So if we go from being concave up to being concave down, that proves that we do have a point of inflection at the possible point of inflection of 3. Where do I substitute in? Original. 3 plus 1 is 4. So it's 4 over radical 3 is where that point of inflection occurs. Questions on the first two? All right, the third one, I want you to go ahead and find the derivatives on your own. I'll be doing it up here so you can check. So once we have those derivatives, the directions say find the point or points of inflection of f of x. And when it says discuss the concavity of the graph, our chart does that for us. Concave up, concave down. That's all discussing of the concavity means. All right, so what are we going to do with the second derivative now? Set it equal to 0. So even before I set it equal to 0, well, let's just show that. Set it equal to 0. Divide everything by 6. You're allowed to divide through by a constant, not a variable, but you can divide by a constant. And we get this. Factor it. Do you know how it factors? Jared?
2x minus 1 and x plus 1.
Good. So there's our factoring. So whatever makes those equal 0, that's going to be the possible points of inflection. What are the possible points of inflection? All right, 1/2 and -1. So now we would have to do our concavity test. I know I'm going to need 3 columns because I have 2 numbers. So I'm going to have to go negative infinity to -1, -1 to 1/2, and 1/2 to infinity. I'll go ahead and make the test value part since we're just kind of starting. So we're going to need to test -2, 0, and 1. Where am I substituting these values in? second derivative. I want to know the concavity. So plugging them in here, I'm going to have a negative times a negative is a positive. Plug it into the second spot. So plugging 0 in, I'm going to have a negative times a positive, so that's a negative. Plugging 1 in, I'm going to get a positive times a positive, so that's a positive. So discussing the concavity, I would say concave up here, concave down here, concave up here. Were they points of inflection? The possible ones, were they? Yep, because our concavity changed. So points of inflection now. See, originally they're possible points of inflection. Now they are points of inflection because we proved it. So -1, back into the original, that's going to be 1. -1 is 0. That's going to be -3 plus 1 is -2. On the 1/2, no need to get a calculator. 1/2 to the 4th means 1 to the 4th over 2 to the 4th. That's 1/16. 1/2 to the 3rd, that's going to be 1/8. 1/2 squared is 1/4. That's going to be -3/4. And then 1. Okay, so to combine these, I can just get a common denominator. I'm just going to have 1/16, 2/16 times 4 is going to be 12/16 and 16/16. So then I'm going to have 3 minus 12, that's going to be -9. -9 plus 16 is 7/16. So you can do that. Don't be lazy and go to the calculator on that. Okay? Questions on anything? Not too hard, right? It's just like critical numbers, except we're using second derivatives rather than first. So your assignment is on the board, also on your assignment sheet. And we're finished for today.